but then that was. Sometimes it gets stupid. And then I just gotta restart it. But I didn't order it. I probably should go to bed.
Fair enough.
I'm still really awake. My laundry's done. This can wait.
I did most of my Astro yesterday.
Oh, okay.
I got a 30 out of 70.
Really upset. I was like, oh, 30 out of 70?
Jace, why is shear flow so easy yet hard at the same time?
Shear flow?
What the hell? I got a 30 out of 70. And now we have an exam on it. The test where it goes over composites and then like shear flow. Yeah.
You see what I was about to share examples today and Friday, which will almost exactly correspond to our summer thing after spring break. He's like, so that way you guys can leave if you have to, but it's beneficial to your research as well. Because it gives you basically like answers. That's why I'm like,
I almost got it. I almost got it.
his face was on the
He had his webcam. Logan, don't hide.
Oh, it's time! Shoot! All right, any questions on the homework? Really? All right.
On 4C, you asked for the solution.
Yes.
But in the question, it's just asking us to write a MATLAB code to get a bunch of values. So you want
So it says see my code.
No, it just
Oh, then it should say. Because you're going to have a plot there, right?
not on 4C. B, sorry.
4B. Can I see? 4B. 4B or not 4B? No, 4B is your code is going to result in set of numbers.
So you put by solution.
Computing numerical values of the expression.
Right.
You got an A, that's 7 numbers. And then you give me the 7 numbers.
Yeah, but I was just.
So that's a solution. And actually, the word should say, see my code at 4B.
Okay, I just, since you said solution, I didn't know if you wanted it.
No, the idea here, let's clarify this for exam purposes especially. If I say solution, that means work has to be shown. If you just gave me these 7 numbers, no points. But if you give me the code at 4B that generated them, that's your solution. So that's what I mean by solution. If I said answer, just give me the 7 numbers. I don't care if there's a code or not. Is it clear? Yeah.
I guess on top of that, then, did you want a plot or table of the values?
Well, what you're going to do is in part C, you're going to construct a straight line approximation and overlay your numbers on it.
Okay.
So that will be the plot.
Okay.
Just the numbers in part B. Yes?
Before C, when it says a straight line approximation, does that mean a straight line in between each of the
It means a straight line approximation. No. The straight line Bode plot approximation. There are no points in the straight line approximation. You look at where the poles are, you look at where things turn on and turn off, and you just draw straight lines, either constant or 20 dB down. Oh, you can draw them by hand.
And you just plot the points?
And then you just put the points on and see how close the points get to this straight line. Any other questions? If only. But I can't. You can't. This should be able to rotate. Never mind. All right. If there are no further questions, then let's turn this thing off and let's go to a YouTube. that was sent to me a while back. Yeah. No signal.
You're gonna send me with a quicker. No, it's good. I still have that curve so
There is a signal, it's just not.
I look forward to it as well, and I'm not even taking
Right. Alrighty. Notice the flapping of the wings?
Whoa.
Right. No, I didn't see that either. So what's gonna, let's play it again. Actually, look carefully at the wings. The tip's going up and down, but so is the middle. All right, and that's important in wings. I mean, the beauty of what you guys have available to you now is materials. Material science is taking a quantum leap. So you can have wings that weigh essentially nothing. Have no natural, little, almost next to no natural stiffness, but they're all controlled by piezoelectrics, which are these little force cells that actually react to strain or stress on a member. So the idea here with this thing is in the framework, simple model for this. That's the fuselage. You got the cantilevered beam, right? Okay. Now the first mode of, if this thing is excited out here, which oftentimes it is due to the aerodynamics, right? You got the flow around the tip of the wave. So what happens if it's excited here is this is the fundamental mode. Up and down, right? And that's at F1. So you, in the frequency domain, you have this magnitude. It's a resonance, right? When the turbulence has a frequency energy at the frequency of this thing, it's going to excite it. But if you watch it carefully, I'll play it one more time, you're actually seeing this mode. You're seeing the middle of the wave also go up and down. It's not just going like this, it's going like this. Watch again. The middle's going up when the tip is going down. All right, that's actually the second mode of this thing. So a model for this thing might be a two-mode model. If you wanted to control the vibration of the wing, you couldn't just use the fundamental mode because that second mode is being excited, as is the fundamental. So this thing may look like this. Does this make sense? And now what we're going to do today is we're going to control it with piezoelectrics. That's a really light aircraft, right? You could stiffen the wing. Well, what do you pay? Well, you either pay a lot of money for the carbon tubes, right, which are really stiff, or you do it with piezoelectrics. So what I did after watching this is I went on to Google and I discovered, don't look at those mails. Don't look at my face. I mean, my face. All right. I don't know how to do Facebook. All right. So what I did was yes, I discovered a 2009 paper by a couple guys from India that used Timoshenko beam theory, the good stuff that you might have heard of actually in your materials course. Mechanics of materials, anybody? Stress, strain. It's all about stress and strain. So this is a very good paper, but it's an 18-page paper. So what I want to do is quickly scan through it, because imagine now, if you will, as Carl Sagan might say, imagine you are an engineer, and you are actually getting paid to do this stuff. Billions and billions of pennies. Fractions of pennies. All right, so what they do is they go through all this is the model, and then what they do is they have 4 quadrants for their patches, their piezoelectric patches. So they have patches along the length of the beam. And these patches are pairs of patches. So if the beam's bending like this, it measures the deflection and it measures the angle, the slope, theta of T. And then the piezoelectrics try to give a force in a moment to straighten that thing out so it doesn't vibrate. So what they then do is they show you 4 pictures. These are the 4 pictures. They've got quadrant 1, which is where the piezoelectric is down at the root, and then up to quadrant 4, where you put it out at the tip. Then at the end, what they do is something really nice for students, is that they only look at 1 quadrant. We're going to put it out at the tip. So they're going to do single input, single output at the end. They actually do it for different locations, but this gets into state space, which we're going to be doing later in the course. So they go through a very elegant development here. And again, this is 2009. This is recent stuff, because these materials haven't been available prior to that time in reasonably priced amounts. So they go through all of this stuff, okay, and you can read all of this. I'll post it for you. Then they do the control system design, so they end up having a matrix. Look familiar? We did this in the beginning of the course, and you did this in 355. X dot is AX plus BU. This is the control law now, okay? And then your Y is your output. So here's state space. You can say, yeah, I know how to get a transfer function from this, right? You Laplace transform, take the inverse of SI minus A, and then you get your transfer function matrix. So there's the A, there's B. They do the control system design, and they do basically a Lagrangian or LQG design, which I'm not going to get into. You can do that in 531. But then they actually show some pictures. Okay, let's go to the open loop response at position 4, which is the tip. Right, because that was the one in the picture that was really going. The middle was going up and down, but the tip was really flapping. So this would be the open loop response. All right, it's very low damped, wasn't it? Right, and you could mitigate this oscillation behavior by damping, but damping takes weight, and weight's everything, right? So if you want something light, damping's tough. So they simulated the open loop response, and then for that same number, they get the closed loop response, which is right here. All right, the amplification. This is the sensor output. This is, let's see, that's it. That's the output velocity. They really reduce the vibration with feedback control. Okay, with these little piezoelectrics. So what I'd like to do now is I looked at the book, and I was going to give you one more example on loop controller design, because we have all the design equations. We went through the DC motor last time, remember? That's right out of the book. The next example in the book is room temperature control. Now, there's nothing wrong with trying to control temperature. I think that's a really interesting topic. But it's an example in your book. And I had way too many professors, especially in engineering mechanics, who take their books and for 50 minutes why am I here? I can read this as well as I'm falling asleep. So you can read the temperature control problem. It's a really nice application of phase lead design. So what I'd like to do today is, rather than getting ahead into nickels, is get into this design. However, before I do, you guys have the advantage of being the new section. Why is that advantageous? One might speculate that that beautifully done dude is a little undone by 3 or 4 p.m. And so at the very least it might be embarrassing to be in the 3 p.m. section. Or you might just be falling asleep more easily, right? The dynamics I have with that group are much, much less than with this group. And I don't think they're that much different as people. I just think it's later in the day and they're burning out. So, before I go to that example that we're going to do today, I want to briefly give you the remainder of what I did in that motor example. I did post it, let's see, it's in the lectures, it's, oh my gosh, this is stats, never mind. Arrow. And let's see, it's the lead lag. Who was it? I don't know if it was this one. There it is. That one. It's getting a little disarrayed at this point. So we went through all of this stuff, right? This is what we did last class for this design problem. And we showed that, lo and behold, we get a pretty good design using this phase lead compensator, right? Okay, but then what I did after the class is I said the following. Okay. Oh, I'm sorry. I got ahead of myself. This is where we ended. And it looks really similar. This is the uncompensated system. The red one is the compensated system. We said, why couldn't we have done this with pole placement design and the root locus? Why are you doing this to me? I'm finally beginning to understand root locus. I might even be able to design a controller using it if I can get these angles all added up right. And now you come and you give me a whole different method when I could have used the root locus to get this done. Why are you doing this? And I told you in the beginning, I teach rocket science and statistics. Lots of students apparently like a little bit of pain inflicted upon them. So I know some of you said statistics, didn't you? Because the professor didn't say they teach statistics. Yeah, I am a professor. I bought my degree. In fact, I ordered it from Amazon. All right, so there's the question. In view of the above, why didn't we simply design a controller via the root locus pole placement method? It seems like we're just learning a new method to get the same results that we would have gotten with a method we already know. Fair critique. Answer, recall that the frequency domain method, and be prepared on your exam, you're going to get this. You're going to get an FRF with no transfer function. It's going to be an experimentally obtained FRF, if you know what I mean. It means I'm not going to go and do any experiments. I don't have money to do experiments, and I don't have the system, this instrumentation. I'm going to fake it. But I'm going to tell you it was obtained from experiments. And I'm not going to give you the transfer function that generated it. So all you have is an FRF. Now you can't do root locus unless you know where the poles of the plant And that, right? You know where your controller poles are going to be. You're going to design your controller. But you don't know where the plant poles are. You have no model for the plant. All you have is this experimentally obtained FRF of the plant. So that's one reason for doing this method. For the test engineer, you don't need to get a model for the plant in order to control the plant. You can do it directly in the frequency domain using a plant FRF, and test engineers get FRFs all the time. But there's another reason for this, and it's a more important reason for you guys, and I mentioned it last time. Suppose that there's a 0.1 second time delay between when the error is computed and when it's received by the controller. Now, 1/10 of a second can be a long time. It could be that there's the controller, the error is being sent via Bluetooth or some channel, but it could also be that it's all wired into the same unit. How do you get 1/10 of a second delay? Well, you have a really cheap processor that's doing 20,000 other things, multitasking. And so it says, yeah, we only need to do this every 1/10 of a second, right? Every 1/10 of a second will be fine because we're doing lots of other things with this little processor. So even if it's on board, you, as an engineer designing, a systems engineer, they may not think that time delay is going to be a big deal. But you can tell them, no. In feedback control, time delays can be death. This is a 0.1 second time delay between when the error is computed and when the controller receives it, and this is the resulting closed loop response. It's in red. What happened? Well, the plant has now e to the minus 0.1 s in it because that's the Laplace transform of a time delay unit. So when we put I omega in here, e to the minus 0.1 I omega doesn't change. The magnitude of this term is 1, isn't it? E to the I theta is 1. So it doesn't change the magnitude of the FRF of the plant at all. What it does is it drops the phase by 0.1 times omega. So if omega is really small, it doesn't drop it at all. As omega gets bigger, it drops it a lot. So this is what happens when you have a time delay in there, and you cannot handle the root locus with time delay. Why? Because the root locus where you give the R locus the open loop transfer function, you have to give the transfer function in terms of poles and zeros. E to the st, no, that's not a polynomial in t. Right? It's a wacky function in t that you don't pay. It has infinitely many poles. And so the problem there is you can't use the root locus very easily, if at all, unless you approximate e to the minus st for small values of omega, and then you do derivatives and stuff like that. But this method is trivial. What happens if this has a phase plot that looks like this? First of all, if this thing has no zeros in its transfer function, which it may or may not, but if it doesn't, what does the phase begin at? This is a concatenation of 2 second-order systems, right? C1 over s squared plus 2 zeta 1 omega 1 s plus omega n 1 squared times C2, so it's 2 of them. There's 2 resonances in the system. It's a 4th-order system, right? Because each peak has to have 2 orders. It's an underdamped second-order system. So the phase would start here at 0, and if it were just 1, where would it end up? C over s squared plus 2 zeta omega n s plus omega n squared. When s is I omega, and I omega is huge, 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 this thing becomes c over I omega squared. You throw this other stuff away. S is dominant. Now what do you get when you have this? You get negative omega squared. Well, that's 180 degrees. So this term goes from 0 to minus 180. This term goes from 0 to minus 180. So the whole works goes from 0 to minus 360. So this starts at 0, goes down to minus 360 in the absence of zeros in the plant transfer function, And, all right, let's do a straight line approximation to this, huh? Real crude straight line. At low frequencies, much lower than this is the break frequency. At frequencies much lower than this, it's constant. Then at this break frequency, it rolls down at 40 dB per decade. That's the slope, because there's two S's, not one. One S would be 20 dB down. But then you get to 1/10 of this break frequency, and let's see. Well, it's not actually doing anything, is it? This is just gonna be a constant. So this thing keeps rolling down until you hit this one. Right? Remember, with the magnitude, it's real easy. All you do is work at the break frequency. There are two break frequencies. The first one is at omega n1, breaks down at 40, then you hit omega n2, and what happens? You get another 40, because you now have s to the fourth in that plant. So this goes from 40 down to 80. Now we want to do the curve line approximation with our freedom curve, which we better use quickly if Trump gets elected. They ban it. We'll have freedom state. All right, what you do is you compute 1 over 2 zeta. That's the Q factor. Authors talk about it in the book. Amplification at resonance is approximately 1 over 2 zeta. So the curve line would do this. That would be my curve line approximation. Okay? So if you have a phase margin, if you have a phase that, say, at gain crossover here is at minus 150, that means you have a 30-degree phase margin, right? You're 30 degrees above negative 180 at the gain crossover. Well, what happens with that time delay? You take the omega times the time delay 0.1, and it may drop it by 30 degrees. Because only the phase changes. The magnitude of that crossover doesn't change. E to the I omega t has magnitude 1. So this is what happened. What happened was the phase margin with that time delay, it dropped the phase margin back down to 21 degrees. Remember, the original phase margin was 18 degrees before we incorporated the lead compensator. Remember? That's back up here. With we did this with lead compensation alone. We had this 21 degree phase margin, or 18 degree phase margin. Yeah, it looked okay. We achieved the right steady state errors and everything, but it oscillated, so we said, no, let's throw a lead compensator in there and raise up the phase margin. We did that. It raised up the phase margin to 45 degrees, and there's the comparison with and without the phase compensator. Or no, well, actually, see, that's the problem. They're almost identical. This is with and without the compensator, right there. And this one is with and without the time delay. So it looks like what the time delay did is brought us back to square one. It's like it canceled out the effect of the compensator. We're now back to an oscillatory step response. Well, that's screwed. Except if you think about the silver lining here, had you not put that compensator in, and you started out with a phase margin of 18, right? So you're at a minus 162. But the phase of the time delay dropped you down by 21. What would your phase be then? Minus 183. You now have a negative phase margin. You now have actually an unstable system. You don't just have a system that you don't like. You have a system that's going to crash. So this is a huge reason for doing design in the frequency domain, controller design, is you can handle time delays like that. All you do is modify the phase plot by omega times the delay d. So it drops down. If the phase is like this, originally without a time delay, And the time, if you start subtracting omega times 0.1, well, at low omegas, you're not subtracting anything. But at higher omegas, you're subtracting a lot, because this is omega, right? And the phase is omega times 0.1. So when omega gets huge, phase gets huge. So the phase drops. So, as I said many times, time delays in aero systems are really, they need to be acknowledged, or you're going to have problems. So I wanted to talk about that, but now let's go to this example. Rather than doing a fourth order system, let's just keep it simple. Suppose in that glider problem we had not seen the second mode. Suppose we had only seen the first mode of the wing doing this, not doing the both modes. Then we'd have a second order system model, right? We want to control that wing. We're going to put the piezo patches on the tip of the wing to control it. But we have to have a plant model for this second order system. And I don't know if you looked at that video very closely. Some of you might have actually picked it up that plant for the wing, the force GP of S, which is the displacement Y of S over the force input F of S. It may have been clear to you, some of you at least, that this was equal to 10 over S squared plus S plus 100. Now, if it wasn't, don't worry. But it was clear to me because I just made that up. All right. So we have a second order underdamped plant. Now we want to design a controller. First, again, I'm really giving you exam material right now, so bear with me. In the theme of the DC motor, let's specify a state. So here's what we've got. Let's do the block diagram before we go further. We have a plant here. It's the wing. We have a wingtip displacement, y of t. We measure that displacement. We feed it back through a controller in the feedback loop. And I'll explain why in a minute. Gc of s. The controller output is what? It's a force. It's measuring a displacement, but then it's computing a force in relation, because that displacement relates to strain on the wing. So it's going to output a force. And that force, this is the controller force, Fc, is going to be, it's going to counter the aerodynamic forces that are exciting the wing. And it's that difference of forces that's going to be applied to it. So if it's like with an automobile, when I had my Triumph Spitfire, 71 Spitfire, I love that little car. You could open up the hood, the bonnet, sorry. The British cars did not have hoods, my friends. They had bonnets. Right? You could open up the bonnet and there were no wheel wells. The bonnet was the wheel well. So you'd open up the bonnet, and then when I wanted to work on the car, I'm sitting on the tire with this little P 1700cc British Leyland engine going, oh, I can reach everything. That's why I hate cars now. You can't reach anything. In fact, you got to be careful if you open the hood, because something, if it's like the battery on my laptop, it may have heated up and it's going to pop out like that video did and grab you in the face and do something very terrible. So, this force counters. When you're driving a Spitfire, I actually tried to design, that was one of my PhD projects when I was in a course, was to design an impact damper for it. An impact damper means when it's basically a lead ball in a canister. Instead of shock, you have shock absorbers, but this is a much more impulsive type damper. When the car goes down, the ball, relative acceleration, bumps it back up, hits the end of the canister. And when the car goes up, lead ball goes down. And I never got to actually build it. We ended up doing, in my graduate course, in my PhD, we ended up doing some simulations and very rapidly learned that this is a highly nonlinear system. And then wrote 2 papers on it. Never built it, though. But anyway, it's the same thing here. If the aerodynamic forces are pushing down on a tip at a given point in time, you want that actuator to push it back up. So you subtract a force from a force. And it's that force difference that excites the tip of the wing, which is your second order model. So let's first of all say that we want a type M closed loop system. What kind of system is this block diagram? Is it a command system? Am I giving it a command force? Only if I'm God. The pilot might not like that force, but I'm in command here. I'm giving you that turbulence. Deal with it. It's for your benefit. No, it's a disturbance system. That force is a disturbance force. You'd like there to be no force there, right? So what's the error? What's the error is E of t is what you want, and what would you like to see coming out of that system? Remember, y is the displacement, it's the tip displacement. What would you like y to be? 0. You don't want the thing flapping around. You want it to just be level. But what do you get? Well, you get y. Okay? All right? So we're going to compute steady state errors for given type number specifications. But now, and I told you this before, I wasn't going to go into type numbers for disturbance systems, at least right away, because you needed to understand type numbers for command systems first. But now, as in potentially an exam problem, to see if you can extend the understanding of a type number, we're going to compute the type number properties for a disturbance system. Remember, for a command system, it's y sub c, the command, right? There's no command here. It's a disturbance. So, E steady state is the limit as t goes to infinity of negative y of t. Correct? Now we're going to go into the Laplace domain. E of s is equal to w of s times y of s, but with a negative. And the negative really is irrelevant in a way. I mean, it's plus or minus. It's just adds a sign to it. Does everybody see that? This is Laplace. At least he saw it. Okay? So here's the error in Laplace. This is the system, the closed loop system, and this is the output. So the error is negative of the output. Or I'm fold. What's the input? Damn. F arrow. Boy, that was a brain fart. Whew. All right, because right, this is the error transfer. This is the error transfer function, isn't it? Remember, for command system, it was 1 minus w, but now it's 0 minus w. Slight difference, but not that big a deal. So now what we want to do is we want to compute the type number. So suppose that the aerodynamic input f of t is equal to t to the m over m factorial. And I put the m factorial in there only because then this is f arrow. Only because then fs of arrow is 1 over s to the n plus 1. Remember, for a tth degree polynomial, when you go into the Laplace domain, it becomes, for an nth degree time polynomial, this becomes s to the m plus 1. For a step, it was t to the 0, right? So the step Laplace is 1 over s to the 1. For a ramp, it's t to the 1. So the Laplace for a ramp is 1 over s squared. Okay? And now we're going to apply the final value theorem. E steady state is the limit as s goes to 0 of s times E of s, but that's equal to the limit as s goes to 0 of what? Well, here's E of s minus W of s. There's got to be an s here, first of all. Let me put the s in the beginning, because that's where I have it there. Times 1 over s to the n plus 1. Everybody on page so far? This is the E of s. I just shoved E of s into this bracketed term. But this s is going to cancel the m plus 1 power of s here. Okay. So then what we get is this. And I'm going to do this. You know what? I'm going to do this. I don't like dragging around negative signs. So let's compute the negative of the steady state error. So I don't have to keep bringing the negative sign on the right side all the time. Then this just becomes this. Right? Got it? Now we're going to put what W is. Let me go over here. So far, so good? You should all know that a feedback system with forward loop G and feedback loop H is G over 1 plus GH. The feedback, we put our controller in the feedback loop. For the reason, aka the block diagram, I want the output of the feedback to be force. I want that force to cancel the input force. And I want the difference in force to be what excites the plant or the wingtip. So now we're going to do the case m equals 0. Suppose m equals 0. So we have a type 0 system. What does it mean to be type 0? It means for a t to the 0 input in force, a constant force, that steady state error will be finite, non-zero. That's what it means. So what you do then, what happens to this when m is 0? Well, anything to the 0th power is 1. 0 to the 0th, but I mean we're letting s go to 0. For anything bigger than 0, this thing is 1. So as s goes to 0, this term is gone. So this whole error minus the steady state error becomes g of 0 over 1 plus doesn't it? So that's if you wanted a type 0 closed loop system. Now what would happen if you wanted a type 1, because your modeling force here is totally static forces. There's no dynamics in the force in a constant force. So, you know, maybe you might want to bump up the type number so that you can handle like small ramps in forces. things that vary with time a little bit. So what if you wanted a type 1 system? Now what happens as S goes to 0? What happens as it's type 1 system. What happens as S goes to 0? You don't say it's 0 to the 1, which is 0. No, 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 no. You take this and expand it through here. Right? So that this term, when S goes to 0, this is gone. 0 to the first power is 0. So what you end up with now is minus ESS is GP of 0 over GP of 0 limit S goes to 0 of S times GC of S. I'm assuming that GP has no poles at the origin. And in our case, it doesn't. It's a second order underdamped system. 2 poles, they're conjugate pair, there's nothing at the origin. So G of 0 does exist for the planet. So this thing becomes what? The GPs cancel out, right? So if this thing is going to be finite, because remember, we said the closed loop is type 1. That means the error is finite, non-zero. It's finite. How is the only way that this thing can be finite? What do you know about the structure of G of S? It has to have a pole at the origin. Because if it doesn't, this thing goes to 0. You have GC of 0 times 0. 1 over 0 is infinite, and you don't have a type 1 system. So for a type 1 system, GC of S must have a 1 over S term. That means it must have a pole at the origin. That means we must use integral control. That's an integrator. Oh, quickly, Peter, quickly. So let's look at this. Well, let's take the simplest controller right now. What's the simplest controller that'll satisfy that steady state error? It's integral control, isn't it? Just K over S. That'll satisfy the steady state error spec, right? And we can choose the K as big as we want so that 1 over K makes a small steady state error and everybody's happy. Except we don't have time. It's so much easier to analyze this controller design using the root locus. So let's just, last 1 minute, sketch out the root locus. The plant has a pair of complex poles. They're very low damp poles. So the root locus looks like this. These are the plant poles, right? They're the conjugate pair from the second order system. This is the controller pole. What's the root locus? Not good. This controller, for small k values, will stabilize it, but will it reduce the damping? No, the damping is going to go up. It's going to, in fact, if you have controller drift, your plane's dead. So we know that this controller, just simple integral control, isn't going to work. So what we're going to do, and we did this already in the root locus domain, we're going to put a pole 0 pair in there. We're going to design a lead controller, but in the frequency domain though. You already did this problem in the root locus domain. Next class, what I'll do is I'll say, let's put a 0 here and let's put a pole here. But we're going to do it via frequency domain design, not angle criterion in the root locus. Remember, the homework's due Friday. If you haven't picked up all the homeworks or exams,